The first comment I want to make about the power rule is that this power rule, although we proved it for only n equals to 2, 3, 4, some positive number, right? But in fact, this holds true for any n. The proof of that fact is going to need some other things that we haven't learned so far. Things like derivatives of the exponential functions and chain rules. So I don't want to actually do the proof. It's quite long. But I think this is just seeing how the proof goes for n equals to 2, 3, 4, and so on could convince you that this is true. So let me actually show you an example when this can be used for numbers other than positive integers. So a few lectures ago, we actually differentiated square root of x. Do you remember the derivative of this?
1 over x.
1 over 2 times square root of x. Okay. This appears frequently enough that you should memorize it. Now, you can actually get this using the power rule. How? Because square root of x is equal to x to the 1/2 power, isn't it? Half power means square root. So instead of differentiating this using the limit definition, you can make use of the power rule and say it says whatever that number is, it has to hop in front. And the number that you put on the exponent should be 1 less than before. So this 1/2 should hop in front. And what's 1 at 1/2 minus 1? 1/2 minus 1 gives you negative 1/2. And then minus exponent means 1 over. And 1/2 power means square root. So you end up with this. Okay? So because it's a multiplication of two fractions, bottom times bottom, top times top, so it's 1 and 2, and square root of x is what you have here. So you get the exact same answer as this, with probably less work. Okay? But still, this is too much work, I think. You should just memorize this. Okay? Try and memorize this. So this is an example where we see that the power rule does hold for n other than integers. You could also have n as a negative number or a negative fraction, 0, 1. It's always true. Okay? This can be used in all those cases. Now let me give you another example of the power rule. What would happen if you differentiate x to the 0th power? It will be 0 times x to the negative 1, right? And 0 times anything is 0. Now, what is x to the 0th power? What's anything to the 0th power? 1. So what we really see is that the power rule is saying that if you differentiate 1, you get 0. Now, is that true? It's actually easy to see that this is true if you remember the definition of the derivative, or the meaning of the derivative. What's the meaning of the derivative again? Slope of the tangent line or the rate of change. Okay? There are two meanings of the derivative, slope of the tangent line or the instantaneous rate of change. And if you use that slope of the tangent line analogy, let's think about the slope of the tangent line of this function y equal to 1. What is the graph of y equal to 1? It's a flat horizontal line, right? Pick any point. What's the tangent line to this graph at this point? It's the line itself, isn't it? Right? So one important thing is that if you draw a line, the tangent line of a line to a line is the line itself. Okay? But we're not talking about the line, we're talking about the slope of this line. What's the slope of this line? Well, we know that because it's the line itself, we know that the equation is y equal to 1. That's the equation of the tangent line. But if you write this in the slope-intercept form, 0 times x plus 1, then we can read off the slope from this expression. It's 0. Right? So what is the slope of this horizontal line? 0. Slope of any horizontal line is 0. Okay? So not only is it true that 1 differentiates to 0, if we use this way of thinking, you can see that any constant, if you differentiate, it's equal to 0. Okay, so that's something in addition. Okay? But power only says 1 prime is equal to 0, but you can actually improve on that and say any constant differentiates to 0. So that's 1. And by the way, that appears frequently enough that you should also memorize it this way. Okay? Any constant differentiates to 0. Still another example of the power rule is what happens if you differentiate x? Okay. X is x to what power? 1 power. So it's like having n as 1, right? So when you differentiate this, 1 comes in front. You subtract 1 from 1. So you get 0. Anything to 0th power is 1. So you get 1 times 1, which is 1. So x prime gives you 1. And in some other cases, it's very easy to use the power rule. Like if it's already of this form, x cubed prime is 3x squared, that's easy. 3 comes front, subtract 1, you get, oh, sorry, I made a mistake. Okay, x cubed prime is 3x squared. That's very easy. But these 3 examples here appear frequently enough, and because it requires some more steps in thinking, you should memorize these. Okay? Memorize these as well as the power rule. Okay, so our list of derivatives are growing. So we already know how to differentiate x to the nth power and some special examples of it. But with just these, there's so many other functions that we don't know how to differentiate yet. So we need some extra rule in addition to the power rule, just to be able to differentiate these polynomials. And that rule is called linearity of the derivative. What is the linearity of the derivative? Okay. It's the following. If you have some constant times a function plus another constant times a function. So you're making new functions out of 2 functions where you have constants multiplied, and you're adding them. You can make, if you have another function, you can put another thing like that in. Such a form is called the linear combination of 2 functions f and g. Physicists like to call this the superposition of 2 functions. fx and gx is superposed to make another function. If you have such a form, then you're allowed to differentiate in an easier way. And the derivative works like this. The constants are kind of ignored. Constants are just there. And f gets the derivative, and g gets the derivative. Okay? So the derivative of a linear combination is the linear combination of the derivative of these functions. Okay? That's what linearity of derivative means. Okay? It's not even hard to show, so let me just do a quick proof. You can ignore this proof if you don't like following proofs, but sometimes following proofs gives you better understanding of what's going on. Okay. So if I wanted to differentiate this function, you first have to replace x by x plus h and subtract the original from it. So that's the left side. Okay. So this we call the left side. Left is equal to that. Then we can reorganize this and rewrite it as, well, AA is common, so I can gather these two and factor the A out. Okay? And BB, I can combine those two, factor the B out. And divide it by H. Now individually they look pretty familiar, right? This is limit H going to 0, A times f of x plus h minus f of x divided by h plus b times g of x plus h minus g of x divided by h. So what I did was I split this fraction into two, this over that, this over that. Okay? And what is this? Isn't this the derivative of f? Right? And this is the derivative of g. Right? So we do have a times f prime of x plus b times g prime of x. That's why this works. Right. Now, why is this useful? Let me give you some implication of this. So suppose I wanted to differentiate, so that's the first example of today, f of x equal to x cubed plus 5x squared. Okay? And then the question is, what's f prime of x? Solution is, well, I'm trying to differentiate x cubed 5x squared. I'm trying to differentiate this. And the linearity says that this is like 1 times a function plus 5 times another function. So I can just ignore those coefficients and just concentrate on differentiating the functions only. So the coefficients are just there, and you're differentiating the function. And then the power rule says 3 hops in front, subtract 1 from 3, that's 2. 2 hops in front, subtract 1 from 2, so it's 1. So this is 3x squared plus 10x. Because this is a multiplication, I multiply them. Now if you compare this with having to do the limit of h going to 0 all the time, this is much faster, right? It's more convenient. So what does linearity mean again? It means that if you have constants in front, you can just differentiate the functions, and if you have addition, I mean, these addition can be split. Sometimes people just think about linearity as two rules put together. One is saying that if you have f plus g two functions, it's f prime plus g prime. Another is saying that if you have a constant times a function, that that's same as constant times function prime. That's another way to view linearity. Okay? If you apply these two rules together, you get the exact same result. Okay? All right. this rule here means not only it's true for plus, it's also true for minus, because if you have a minus, that can be thought as plus of -1 times g. Right? So subtraction is also can be worked this way. You can also have several additions. So f plus g plus h plus I. That's still okay. You just have to differentiate individual ones. Okay? You can apply this rule over and over again to say that if you have 4 or 5 functions, you can differentiate it individually. That's another possibility. So let me give you another example. Example 2, f of x equal to x squared minus 5x plus 7. Okay, what's f prime? And the solution is you differentiate x squared, so that's 2x, and then you differentiate x, right? And then you differentiate 7. Okay. Just maybe I should just leave it like this: x squared prime. So you just differentiate individual terms like that, and that gives you 2x. What's x prime? 1. We just had it. What's 7 prime? Yeah, constant differentiates to 0. So this is 2x minus 5.